would like to welcome you all to our panel discussion tonight on the topic, how can mathematicians contribute to planetary challenges? I would like to thank the IMU for making this panel possible and getting it on the schedule on a rather late notice. And I also would like to thank my 5 panelists here for coming here and being such great cooperators in getting this to start. I'd like to start by suggesting to the panelists to introduce themselves briefly with a microphone. So, Amit, you get to start.
Okay, I'm Amit Apte. Okay, I'm the first one on the slide. I'm at the International Center for Theoretical Sciences in Bangalore. I work on dynamical systems and data assimilation problems. And I'm also interested in various activities related to the Mathematics of Planet Earth program that happened 5 years ago and continues now as a continuing activity of, for example, the ICM, as well as outreach activities in mathematics. So that's a brief introduction.
I'm Pedro Silva Dias. I'm a professor at the Institute of Astronomy, Geophysics, and Atmospheric Sciences. And my major interest is in more theoretical aspects of atmospheric dynamics. And that's basically how I got initially in contact with the applied mathematics. And also I have an interest in numerical weather prediction. And then, of course, in issues related to algorithms for operational weather forecasting.
My name is Maria Esteban. I work in Paris at CRS and University Paris Dauphine. I work in nonlinear PDEs and mathematical physics. And I think my proximity to this kind of topics is through my involvement in the International Council for Applied and Industrial Mathematics, of which I am president currently.
My name is Edward Lungu. I am from the Botswana International University of Science and Technology. It's a new university. Nobody has heard about it. You are hearing it from me. But I am one of the oldest mathematicians in Africa. I have worked in biomathematics, hydrology, ecology, several other areas. So I'll be here to give you examples of what has gone right and what has gone wrong in Africa, and how we are using mathematics to control and even to understand processes. So that's why I am here.
Hello, I'm Claudia Sagastizábal. I'm adjunct researcher at Unicamp in Campinas, Brazil. And since my PhD, I have been studying energy problems with an emphasis in variational analysis and optimization. And all these challenges that are now involving moving from the traditional way of using electricity and generating it to the new ones in a sustainable world is a challenge that I think is very interesting for all mathematicians.
And I'm Hans Engler from Georgetown University. I'm an applied mathematician. I also want to direct your attention to the very simple, at this point, website where these slides can be found, mathplanetarychallenges.wordpress.com. And there's a short version of the URL that takes you to the YouTube site where you can see the video that was produced for this panel. And you don't have to scramble to write it down. It'll appear again a number of times. I'd like to begin by maybe not offering a definition, but by talking about what are planetary challenges. It's really a default definition, as it were. Challenges, problems, tasks, also opportunities which go beyond national boundaries, perhaps because the underlying causes or mechanisms that amplify phenomena transcend national boundaries, They are goals which are therefore often beyond national capabilities, and they are problems which often are beyond single scientific disciplines. They are issues that may involve not just physical and biological and life science or economic issues, but even social and political science issues. The image that you see there to the right in the slide is an image from a concept called the donut economics. You have a green ring, which is the donut, which is where humanity is supposed to be, an outer ring, which contains physical constraints and environmental constraints and physical processes which constrain us, availability of water, availability of energy, things like that. And in the inside, there is another ring with social needs, with goals that are desirable for humanity. So, as it were, mathematics sort of is sitting in the middle, and it's a mathematical picture. So this shows that mathematics as an international enterprise and universal human science, as it were, with universal applications, definitely will have a role to play in meeting these planetary challenges, and I hope tonight's panel discussion will actually show you that some of these challenges are already successfully met, and where there are challenges which we can do better on, and also where there are perhaps opportunities for mathematical work. So here are maybe 5 slides total, which will give you a brief overview of what we're looking at here. So one theme is food and water. Everybody needs to eat, everybody needs to drink, sanitation, water for agricultural production. There are over 7 billion people on the planet right now. Out of these, 3 billion are probably malnourished. That is, they either don't get enough calories or not enough nutrients, or maybe not enough of both. On the other hand, there are probably 2 billion overweight or obese adults. The intersection between those two sets is non-empty. You can be malnourished yet overweight. The growth of the population currently is about 1 billion people every 10 to 12 million, 10 or 12 years or so, and people are getting also wealthier, so their dietary demands are changing. People want to eat better. About 30%, on the other hand, of all food that is grown probably is wasted in some form. This may be because it drops before it gets harvested, it drops on the ground and rots, all the way to it being thrown out of the fridge because it has reached the limit where you don't think you can eat it anymore. So that is a big, big, huge waste. Fresh water, the other big resource in this title here, is used, as we know, for drinking, sanitation, cooking, agriculture, aquaculture, also for industrial uses, for many processes, and even for energy production, for cooling purposes. All these uses are competing. There's a limited amount. Next, energy and climate. I'm lumping these together because climate, in particular, the change in climate that, as the universal scientific consensus is driven mainly by human activity, that is happening because of energy use. In the top right corner, of this image, you see a piece of the Keeling curve, which tells you what the monthly averages of CO2 data, CO2 content in the atmosphere is as measured in Hawaii. This curve is increasing. It has a positive second derivative, roughly speaking. It also has a seasonal variation, and the curve ends in 2008 or 2009. It now has reached about 410 parts per million. This continues to grow. On the other hand, renewable energy sources are disrupting markets. So wind energy is already cheaper than coal energy, certainly in the United States. The problem is it's more intermittent. You cannot just turn it on and off. You have to store it. But the energy price market is definitely changing, and we hope to hear a little more about that tonight. A big role of mathematics has already played in global climate projections for different scenarios. the spatial resolution now is about 1/4 of a degree, so that means that the climate prediction for this part here of Rio is going to be different than the one for the climate at the Santos Dumont Airport, for example. That's a little more than 1/4 of a degree separate. So climate models can resolve these spatial scales now, but there are many, many uncertainties, in particular in the modeling. Health, many aspects of health. Everybody thinks of their own health problem, of course, when this happens. Malnutrition continues to be a big, big problem. About 1 million children die per year because of malnutrition. This may not just be a lack of food, but also tainted food, food that is maybe somehow polluted, or food that is deficient. And 200 million children, probably under 5, are too short or underweight for their age on the planet at this time. That number will probably grow up. Chronic diseases and epidemics are also a big problem. Cancer and cardiovascular diseases are on the rise, in particular due to better, longer longevity, increasing longevity. So there's an aspect of modern medicine that has, unfortunately, a negative side effect. Epidemics such as HIV/AIDS, the single biggest killer worldwide right now. Diarrhea diseases, which are very different from HIV/AIDS, but and can be handled. Tuberculosis, malaria, which is a big problem in many parts of the world. And there are emerging diseases and changes in the disease patterns, and partly due to changing behavior of disease vectors like mosquitoes. These include Zika and Ebola. Those are in the news. They are bringing a lot of heartbreak and misery to people, but they are not the big killers. Antibiotic resistance is lurking in the distance, in the shadows, and will make everybody's life much more dangerous also in the future. Another planetary challenge. Communities. Here I'm lumping together trends such as the increasing urbanization. 1 in 8 people on the planet, that's 1 billion or so, live in mega cities, cities that have urban conglomerations that have more than 10 million people. The last 3, including this one, ICMs were all in the mega cities among the top 100. Of course, 2002 was in number 3 in Beijing. Traffic migration and transportation issues are consequences of this. They are very, very amenable to mathematical modeling. Well, to some extent at least. Economic opportunity and inequality follow and drive some of these patterns. Those are much harder to model mathematically. And of course, then you have worldwide virtual communities, which are often springing up out of nowhere within months or so, driven by social networks and social media. Life on land and in oceans is something that many of us think about. Up there you have a picture of a flooded piece of jungle near Manaus. And here's a mathematical question for you. How many species are there that we have not yet observed? That's like how many pennies are there in the dark that you have not found yet? It's a statistical question. It can be solved, by the way. There's a food web picture there, again, to suggest mathematical modeling, and a picture of that shows the effects of the combined effects of surface flows on the ocean and pollution, garbage patches. I'd like to direct everybody's attention, if you haven't already noticed this, to the United Nations Sustainable Development Goals formulated and agreed upon in 2015. That's a matrix of 17 goals here. These are political goals, starting with eliminating poverty, hunger, and improving health for everybody. While they are political goals, they will no doubt drive decisions about development, research, and also data collections. So if you're working in this field, even as a mathematician, you need to be aware of these. They also segment the sets of problems that we are looking at rather neatly. Mathematicians, by the way, are already playing a role in here. Just last week, I sat in a talk by somebody who was one of the advisor people for Go number 15, mathematician. There has been an effort going on already about mathematics of planet Earth. Amit already mentioned this, and Christian Rousseau, who's in the audience, has been instrumental in getting this started. There was an international year organized by many international mathematical societies about 5 years ago, with many activities and events all around the world. The Society of Industrial and Applied Mathematics in the United States has an activity group on this theme now. The European Geosciences Union just changed its section name on nonlinear geophysical processes to mathematics of planet Earth. So it's a topic, a brand, as it were, a name that is becoming more and more common. So I've talked a lot about us now and about what perhaps my personal view is whether these challenges are. I have some questions for you. So please raise your hand if you have done some math, not the panelists, I know what you've done, but in the audience, please. Raise your hand if you've done some mathematical work related to one of these topics. Okay, thank you. Here's another question. So I'm going to go down these 5 topics here. Please raise your hand if I'm calling out an area that you think is either important to you or where you think you probably would be interested in working if you had the opportunity, or that otherwise you think really deserves emphasis and attention. So food and water. You can raise more than once. Yeah, you can raise more than once. Yes, I'm not going to, I just want to get a visual idea. Next, health. Energy and climate. Then broadly communities, cities, transportation on that theme. Okay, I see some people raise their hands every time. That's nice. And then life, broadly. Okay, thank you. Finally, in case you haven't worked in this area yet, or you're thinking about it, or you're already doing it, do you know how to find partners or to find opportunities to work mathematically on one of these areas? If you know that, if you have an idea how to do that, or have done it already, please raise your hand. Okay, thank you. All right. We'll now go into a round of 3 or 4 questions which are directed to all or some of the panelists. And the panelists will pass a microphone around. Everybody will hopefully contribute something. After that, we may have some more questions which are directed at specific panelists, but there will also be time for questions from the audience where the microphone will be passed around, directed again at the panelists. Let's begin with the first question. What are the roles that the mathematical sciences can play in addressing planetary challenges? So let's see, where's the microphone now? Over there. So Pedro, do you want to start?
Yeah, when I received these questions, I decided I could talk hours about this, but I chose 4 topics. The first one is the development and validation of numerical models. This is something critical in the sense that weather prediction models, it's an initial value problem, but it's a huge dimension. Modeling climate, for instance, it's not just the atmosphere, it's also the ocean, the ice, the trace gases that are floating around, like the pollution issues and so on. The vegetation, the biosphere plays an important role in controlling climate. So it's actually a physics and a multi-scale problem. And in order to do it efficiently, you have to provide weather forecasts or climate predictions in a very short time for the users to be useful for the users. And it often requires the development of new algorithms that are sufficiently efficient in order to provide the results in a very short time. And there are several examples in the meteorological history of the interaction with mathematicians who provided major advances from the point of view of the numerical schemes. The second topic that I wrote down here is the big data analysis. There's a deluge of information nowadays coming not only from the remote sensing systems, new satellites that have really high resolution with poor data, very large scale, and we have to get some meaning of this information. And also data that comes from models in order to extract useful information to transform a meteorological information to something useful for agriculture, for energy managing, for managing big cities, etc. So transforming raw data into action. And there are also several examples of the use of artificial intelligence and so on that are related to mathematical advances. A third one that I'm particularly interested is this issue of data assimilation. Data assimilation is the bridge between the product of the numerical models and the observations. So you have a state variable, let's say it's x, and observations, let's say it's vector y. And the problem is that the state vectors in most of the climate models is now running of the order of 10 to the 10th power. And the observational vector, it's of the order of 10 to the 7th power. So there's a gap there. And you have to find some way to optimize the definition of the initial condition, the state vector x, based on a much smaller amount of data. There was a lot of theoretical advances that were made in the 80s from a theoretical point of view. Mathematicians did play a very important role at that time in this initiative. And that initiative that was put together in the 80s, published in the 80s, actually became operational in the beginning of the 2000s. And if you look at the quality of the weather forecasts, there's an almost discontinuity in the quality in the beginning of the 2000s because of the introduction of these techniques that were theoretically derived almost 15 years earlier. It would be basically impossible. When I started my graduate studies in the 70s, for instance, if you told anybody at that time that we would be able to have weather forecasts up to 10, 15 days with reasonable quality as we have now, it would look like a dream, you know, something completely out of the reality at that time. And it became feasible in the beginning of the 2000s. Actually, it drove the World Meteorological Organization to put together programs to have more interaction in the international community, and interaction not only among the meteorologists, but also with the computer science people, the mathematicians, to develop new techniques, so that what the meteorologists usually call the seamless prediction. In other words, going across the scales in one single model. The challenge, the mathematical challenges in doing that, they are really great. And a fourth topic that I think is very important, and where mathematicians also played a very important role, is dealing with uncertainty. mathematical problems arise in atmospheric research are very diverse, as the problem is one of stochastic prediction for which error in both the model and the observations need to be considered and estimated. And the challenge is the dimension of the problem, 10 to the 10th, that's the state vector. So there are several techniques for smaller dimensions, but for big dimensions, it still requires a lot of research. And finally, what we call the toy models for the climate variability. Understanding climate variability is fundamental, including this issue about attributing causes for climate change, whether it's natural or whether it's human-induced. So toy models are fundamental. There are several thermodynamical constraints that require the application of optimization methods to really understand. In understanding the role of nonlinearity, how energy goes from one scale to another. I'm particularly interested in this issue. I had students who have published papers showing that, for instance, the diurnal variability, the diurnal cycle, which is obvious, I mean, the sun goes up and down every day, interacting with what meteorologists call the synoptic scale, 5 periods of the order of 5-7 days. In other words, the interaction between the diurnal cycle and the 5 to 7 day cycle end up producing what we call the intraseasonal variability, which is the order of 20 to 60 days. So how can you get energy flowing from these fast scales of diurnal to the intraseasonal? And at the same time, you can have very interesting examples of mathematical processes that explain how energy goes from the, let's say, the intraseasonal time scale, 20 to 60 days, interacting with the annual cycle and the what's called interannual, the niños and niñas that most of you are aware of, putting energy, transferring energy to the decadal or multi-decadal cycles. This is particularly important for understanding what is the role of the human-induced change in climate, how you're going to change the long-term climatic variability. So there's a huge number of examples where mathematicians play a significant role in improving the quality of the weather and climate predictions.
Thank you. We'll hear from Claudia now. We have a little over an hour, so I think we have time to address these things in detail, but at some point we'll have to speed it up, I think.
Okay. So regarding energy, an important role that we mathematicians have is that we give credibility to decisions that are taken by governments, some kind of technical backup, let's say, and this is very important. Also, the fact that when we contribute in the definition of the models and the computational tools that solve these problems, they can be repeated and they're always the same. This is very important. I have an example some years ago here in Brazil. Brazil is very advanced in how to manage hydro energy because there is a huge potential of water here, and it's used for generating clean energy. But it is uncertain, as Pedro duly noted. El Niño and La Niña disturbed all the forecasts that were used to see this kind of, to model this kind of phenomenon. And at some point, some years ago, the models gave some very strange price That is how the energy is commercialized, and this is why the generating companies want to produce it, and eventually we have electricity in our homes. And it gave a very, like an outlier, very high price for the next, I don't know, 2 months ahead in some region in the north. And because of that, many managers decided to invest and to do things in that direction, and eventually this didn't happen. And they were fired, and it was a big scandal. And because of this, we started to analyze what was going on, and eventually it was some wrong, not wrong, but not well applied interpretation of the Borel-Cantelli lemma. You know, the one that in non-mathematical terms says that eventually if you live with computers or typewriters, a set of monkeys, they will type perfectly the whole of Shakespeare's works. So this is some probabilistic lemma. And it was not being well applied. The algorithm was being stopped based on this wrong interpretation, and because of that, this gave a very bad price that put into trouble quite a lot of important institutions, let's say, in the business. And thanks to because this happened, we got to look into that with many international also partners, and this was solved. So it is very interesting, this kind of interaction that we have with practitioners who really have passionate problems, and then the deep theorems that we can also work on top of this phenomenon that we observe. So that is something really challenging, and how I see that mathematics can help.
So I will talk a little bit about data assimilation again, because that's one of my main research areas. But let me start by talking about, for example, the role that mathematics can play in a area related to what Pedro talked about, but that's closer to home for me, monsoons. So phenomena such as the Indian monsoon is still not very well understood. There are various reasons for why it is not understood. The clouds are not well understood. Large-scale structure and large-scale organization of cloud systems around the Indian region is not well understood, and because of which the prediction of monsoon rains is still still poorly done in using even the best models in the world. One of the ways that we see the lack of there is no good understanding in terms of simple mathematical models of what exactly the monsoon phenomena is and its relation to other planetary phenomena such as El Nino, La Nina, and related to oceans. So such simple mathematical models are completely missing, which makes it difficult to diagnose where the large-scale models are actually not going well. There is very good examples in other systems such as the Atlantic Atlantic oscillations and El Nino, where simple mathematical models have given good insights into the actual phenomena and hence led to improvement of the prediction of these. And that's one of the places mathematical modeling using simple simplified equations, simplified models, not in terms of model reduction, but simplified models that capture the essence of the phenomena is a big challenge. I mean, it's a big part of mathematical modeling, and that can be applied in complex systems such as the atmosphere and the ocean as well. The second point I want to talk about is data assimilation, which is what I work on. In particular, as Pedro mentioned, the mathematical development of data assimilation, in particular development of Bayesian methods on infinite dimensional systems, because eventually we are dealing with partial differential equations for atmosphere and ocean. And so the Bayesian methods developed for these infinite dimensional systems, eventually leading to better algorithms, is one of the key ingredients in improvement of data assimilation. Recently, there is also a fair bit of work on trying to relate optimal transport problems to data assimilation and filtering problems in general. And the third aspect is looking at the dynamical systems theoretical challenges. So the instabilities in the system and how that affects data assimilation. So these three, so to say, mathematical concepts are directly related to improvements in data assimilation, but there is still a lot to be done. In fact, one of the review articles about 2 years ago mentioned that in the short term, these methods will give good results, but in the long term, maybe 5 to 10 years, completely new mathematical ideas will need to be developed to improve data assimilation significantly. So that remains to be seen how that plays out. Yeah, I think
So today I decided not to speak about particular topics, but speak in general about how mathematics can help in dealing with planetary challenges. So in order to answer these questions, I would say that mathematicians, based in as good as possible models and in alliance with other scientists, what they can do is to help quantifying the evolution or impact of natural or man-made or industrial processes. So in order, and then once they quantify them, they can make predictions, they can assess risks, they can alert decision makers, and so for me this is the main thing that mathematics can do with respect to planetary challenges, to base themselves on models, do scientific work and rigorously, and based on that help to make the good decisions.
Thank you. You know, my colleague Amit has come from the monsoon, so he has lots of water. And I'm coming from the desert, where we don't have much water. And yet our economy, you know, in Botswana and the surrounding countries depend, you know, on wildlife. We have a vibrant tourism industry, but we also have a vibrant, you know, domestic livestock industry. But we don't have much rain and therefore not much grass. So there is competition between wildlife and domestic livestock. And from time to time, maybe once every 5 years, we have to determine whether the animal population on both sides, you know, can be sustained by the little grass, you know, that is available. So we have been using, you know, stochastic differential equations, you know, to find optimum levels, you know, for these two species. And it is very, very important for us because both domestic and livestock, you know, economies, they are supporting our industry. We cannot afford one of them, you know, to go down. That's one. Then the second problem where mathematics are playing a very important role is in diseases, both for humans and animals. Now, for animals, it's very complicated because they do not understand borders. So they move from one country to the other. They don't need a passport. But the result is that if a disease starts, you know, in one country, it will spread, you know, into the other country. So we have to find ways, but it is not that easy because elephants do not like not to be controlled. And even if you try to stop them from going from one country to the other, they would rather fight you rather than go back where you want them, you know, to go. So it's not an easy problem finding ways of providing, you know, or separating, you know, migrating wildlife from domestic livestock, especially the buffalo. Buffalo and cattle, you know, will mix freely. So, but the other thing that mathematics are, you know, becoming important for is in Africa where energy is scarce and people depend on the forest for energy. They are cutting down trees to encourage them, you know, to use electricity you must price the electricity, at the right price. So what is the right price? That's what mathematicians are working on. So these are some of the topics that, as we go along, that I will expand on. Thank you.
Let's leave the microphone at that end because that's where we start for the next one. The next question is really about new opportunities for mathematical research and interdisciplinary work. Those are two different things, right? Mathematical research is when we publish in the Annals of Probability or in Archive of Mathematics, or interdisciplinary work where you might publish in the Journal of Quantitative Spectroscopy or a place like that. So where are there new opportunities arising from planetary challenges? Where is there perhaps opportunities for new and exciting mathematics? We've heard a few of these things already in terms of challenges, but maybe some of our panelists can just focus on one or two opportunities that they see. Edward, do you want to start?
Well, thank you. As I said at the beginning, we are a new University of Science and Technology, and our government, expects us. I don't know whether it is just an expectation or whether they want to see us lead the other sciences. So we are heavily involved in the earth sciences, and I want to split the earth sciences into two. We have the usual environmental science, that's ecology and the other areas, and I did talk a little bit about wildlife and domestic livestock. So the government wants us. That multidisciplinary nature in a desert type of climate is very, very important. But we also have, the biotechnologies, not just the general teaching of biology, but we are talking about the biotechnologies, how we can engineer new foods, from maybe existing seeds, changing them so that we can produce food faster, so that we can produce more nutrient food. Our university is tasked, to do that. So there are several multidisciplinary approaches where our government expects mathematicians, to be involved, because it is a tool that they believe will bring about, effective change. For a long time, we have worked separately, mathematicians on their own, chemists, on their own, but that is changing. We want to see, forensic scientists, working, with computer scientists. We want to see biotechnologists working, with computer science and mathematicians. So we are in the process of arranging ourselves to ensure that there are opportunities, for mathematicians in the other areas where they didn't think, they were needed. And actually, it is paying dividends so far. Thank you.
So I think that there are new opportunities in all areas that you quoted at the beginning. I think I'm more interested in questions related to energy. There is a lot to be done about energy. It's not only to find new ways of producing energy in a cleaner way, but it's also to use less energy, or to use it in another way. And in that direction, I think that we are speaking, or we hear about people speaking about smart cities nowadays. So smart cities means designing new urbanism rules that allow us or empower us to use less energy, and this is through the use of better materials, limiting pollution, limiting the use of energy, polluting less, designing better the networks for distribution of energy, etc. So I think that the Smart Cities program that is really a global problem, and I think that energy combined to smart cities is for me a very interesting area, because there are many problems coupled at the same time that have to be designed and solved.
Yeah, so apart from the areas which I mentioned earlier related to data assimilation, I feel the impact of natural phenomena, climate change and so on social phenomena. So how does society respond to these natural phenomena? Mathematical modeling related to that will require a lot of interdisciplinary work and possibly thinking about very different types of mathematical models in order to assess these impacts in a quantitative fashion that can actually hopefully affect the policy making in the future. So,
following what Maria was commenting, smart cities also pose a problem of privacy protection of data. For example, this is something that was not present in the landscape of what energy meant. Also, we are now looking at the energy problem from a much broader and a larger perspective, because of the intermittent sources that cannot be stored, and then a form of storing wind, for example, is being done in Denmark. They heat water and they put it under the underground, and with that, the wind of I don't know that blows in summer is used to heat houses in winter, and it's really a big saving. More than 50% of the energy that is used in winter is from that source. Before we didn't think of that, and because of that, we have to include in our models all the heat networks in addition to the energy networks. And so there are very challenging optimal control problems, differential dynamic systems that have to be controlled in a sound manner. So, well, once again, it's a fascinating subject with many challenges.
Okay, in a slightly different directions, I'm going to talk about from the point of view of opportunities. And one of the points, of course, the threat of climate change is something that we have to be worried about. And there are some new players in this process. For instance, the insurance business is very much interested in finding out the risk associated to climate change. And I know of companies in the insurance business that are funding research in this area. And I think this is something, a very interesting opportunity. And of course, it requires interdisciplinary cooperation in order to do this kind of study. As mentioned before, the challenges associated with the growing use of renewable energy. The Brazilian case, I think, particularly interesting because we have the hydroelectric, wind, solar, and biomass. The opportunity that I see here is the resources that are available from the energy companies. So, and in Brazil in particular, the law requires these companies to invest a certain percentage of their resources in research, and we haven't been using totally this large amount of money that is available for research. But of course, you have to do things in cooperation with different disciplines in order to put together a system that provides what they need in order to have this optimal use of all the renewable energy forms. The third point that I think we have an extremely interesting opportunity here in Brazil is issues related to the applications of, for instance, climate or weather issues in the agribusiness. As you know, agribusiness in Brazil is a major component of the national economy. And something that I find very interesting is how in the last, let's say, 10, 15 years, the private sector became more interested in new products that involve cooperation among mathematicians and in atmospheric sciences, in agricultural sciences, and so on. We have to really explore this opportunity because funding from the traditional federal organization is becoming much more difficult. So we have to deal with this kind of opportunity. And finally, something that I was away from the University of São Paulo for almost 8 years. Then when I returned, there was something that surprised me. Is the fact that even a traditional institutions such as the University of São Paulo is becoming much more supportive of interdisciplinary sciences. For instance, this issue about joint appointment. If you are in a department or in an institute, you can have a joint appointment with another institute. In other words, interdisciplinary studies. This used to be something really difficult here in Brazil, and now it's becoming more acceptable. And I have in my institute, for instance, I have examples of people who have joint appointments, which I find it great in order to produce new science, something that has a significant impact from the societal point of view.
Hello? Okay. All right, question 3. This is a specific question. How is mathematical modeling done in work on planetary challenges? This is a huge field. So we decided beforehand to have start with 2 panelists. One talk about generally mathematical modeling for those in the audience who may not be applied mathematicians, and then hear a little more about one specific application from Pedro. So let's pass the microphone over to Maria, who will start.
Yeah, thank you very much. Yeah, when we discussed a little bit about the preparation of this panel, I thought that maybe there would be people here who come from areas of mathematics that they don't know what is modeling. And I don't think that modeling in planetary challenges is different from modeling in other areas, industrial, applied in general. But I know for sure that there are here people that they don't. I mean, we are speaking of models, and what does it mean? So for people who don't know what modeling means, sorry for the other ones that know perfectly what it means. So a model is a way to describe reality in a quantitative way. Okay, so you have something, you have a phenomenon, you have a process that you want to describe. And so suppose that it's a new thing that you want to work in, so first you have to understand the problem. Understanding the problem often means understanding things in fields that are not mathematical. So it can be some biological problem, a medical problem, or mechanical problem, whatever. So in general, at the beginning, you have to start reading a lot about this problem, trying to understand what it means, what is important in the description of the phenomenon you want to model. You have to discuss with experts. All this means that you are going to spend a lot of money, spend a lot of time preparing yourself for the modeling and working on the model. And that's a problem for mathematicians because this time that you spend doing that is not going to be measured when you will go out for hiring or promotions. So this is a problem that we should address also here. Anyway, so you spend some time preparing yourself to deal with a model, to build it. Often the models are built by experts in other fields. Sometimes they are done jointly by mathematicians and people in other fields, okay? So it depends on the problems. So once you, for example, want to model a phenomenon, I don't know, the evolution of tumors, cancer tumors, something like that, you can work with doctors. They explain to you how they perceive it, how it works, and you try to build a model. So what does it mean to build a model? It means to find mathematical tools or language in which you can describe the phenomenon you want to study. It means choosing the mathematical language or sub-language. You can use maybe dynamical systems or PDEs or probability statistics or optimization. I mean, you have to, maybe based on what you know, which kind of mathematics you know, you have sometimes to ally yourself with people in other fields, and then you write something that describes in a quantitative way the phenomenon you want to study. So in general it means, for example, a set of equations or some energy function you want to minimize or things like that. So a model can be good or bad. A model is an approximation. So you need to decide the level of approximation you want to use to describe the phenomenon. And the model is evolving. It's not a model you write forever and you are going to work with it for a long time. I mean, sometimes you decide the level of approximation and then you have to include more and more details. When you study your toy model, then you can approach the reality better. So this means modeling. It means finding a quantitative way, a way of using mathematics to describe a phenomenon or a process. I don't know if it answers what you wanted.
Thank you. Now let's, we have 3 slides. We'll probably only have time to go to 1, maybe, or 2, prepared by Pedro, which show a little bit about how this actually, what the scale of the problem is specifically in meteorological and climate modeling, I guess. So let's go to the next slide right away. This one here, yes.
Yeah. For instance, this set of equations on the left-hand side represents the complexity of atmospheric modeling in the sense that you have a set of equations for predicting, for instance, the atmosphere, the first one, ocean, hydrology and ice, the second equation, the soil. The soil is very important in terms of energy, and the vegetation, because that's how the surface interacts with the atmosphere. And then the chemical species. And each of these X variables are huge, in the sense that they are of the order of 10 to the 9th, so 1 billion or 1 trillion, depending on the case. And the uncertainty actually comes from the stochastic and unresolved processes. That's the lower figure on the left. So you have uncertainty in the initial condition, and you have to deal with uncertainty in the model formulation. Both lead to the final uncertainty. And the figure on the right is what I mentioned before. It shows the change in the quality of the weather forecasts from the early 80s to now. And as you can see, at the top, for instance, it's the short-term forecast, and in yellow at the bottom is the 10-day forecast. As you can see, there's this continuity around 2000, 2001, 2002, when the forecast, the quality of the forecast in the southern hemisphere, which is the lower part of the blue part of the figure, and the upper part of the blue line is the northern hemisphere. They merge together. And back in the 70s, 80s, 90s, everybody would used to say that weather forecast in the southern hemisphere would be hopeless because you didn't have as much data as in the northern hemisphere. But then suddenly, in the early 2000s, you get pretty much the same score in both hemispheres. And you know why? Basically because we learned how to do data simulation using satellite data. Satellite data sees both hemispheres. So this was really a great improvement of weather forecasts.
Thank you. Let's pass it over to the other 3 panelists so we hear from each of them a little bit about new challenges.
About models, I want to say just give an analogy. When you go to work commuting from one place to home, from home to work through a highway, your model of the way is just this highway. You don't need to know the names of the streets that are surrounding the highway because you never get out. And this is your own model of what is the way to home, or depending if you are leaving work or to work. But if there is a traffic jam, then you will want to get out and have a better description of what are the little streets around the big highway because you want to go to your destination. So this is how models evolve. We start with some simple description of the phenomenon we want to understand and then, or to control. And then little by little we learn more knowledge thanks to the discussions with practitioners and this interdisciplinary work. Many times it takes time to get to a common language. I see mathematics as a language that we all speak with certain accent. And then with different disciplines, there is some different dialects, and then eventually you get a common, after working for a while together, you understand each other. What is it, what you mean when you say some word, because it's not always straightforward, it takes some time. And then you can make a better model with this new knowledge. So models are always evolving and improving. They are not perfect, but they are useful.
Well, I'll be very brief. You know, one of the first slides, we had mentioned Ebola. So when we talk about mathematical modeling, that is a very good example of how difficult, it can be. Because when Ebola starts, you do not have any data at all. And even when you construct a mathematical model, you cannot even use any data, to estimate, your parameters. So it becomes very, very complex. And in the beginning, the estimate was in West Africa, which is about 2016, 2017, the estimate was Ebola would be cleared in 8 weeks. We all know it took more than a year to clear, the disease. That's how complex it is, and that's why it is important to understand the dynamics, first of all, and where there is data, use the data to find the proper parameters, and then see whether the dynamics of the disease are properly reproduced. So that is mathematical modeling. It's not always, an easy subject, because it depends very much on other things, especially data. Thank you.
Thank you so much. I think we'll skip through the next few questions and now give the audience an opportunity to ask questions. So here are the traffic rules. There's a microphone that should be passed around. Please use that. Please identify yourself briefly, where you're from. And please also keep your question short and concise. Just one question, and keep it short. And then we'll pass it on to one of the panelists. So if you have a question, please raise your hand.
Thank you. So I am Vincent Laforgue, and I am a pure mathematician with a first background, in fact, in operator algebras. That's my first mathematical subject. And I would like to ask the following question. Progresses in solar panels, batteries, climate studies can be realized by collaborations, for example, between a mathematician, a physicist, and a numerician. Can we help them interact? Could we have one or several websites where motivated mathematicians and numericians could indicate their competence, and physicists, biologists, chemists could indicate the kind of mathematics they need? Which institutions could host such websites? For example, with my background in operator algebras, it's not obvious for me to find how to contribute to quantum mechanics for solar panels or batteries. Thank you.
Thank you. So this is about really a question about communication between mathematicians and other scientists or stakeholders maybe even, specialists in other fields. So any volunteers from our panelists?
I think that these collaborations come from very informal, you know, you are working in an area and you know people or you look for people, but I don't think you look in websites necessarily. You have connections or you ask people about how to find others that can help you. There's been how policy about it. For example, I remember some years ago about solar panels and solar energy. There was a call made by the NSF where they were calling for applications where there should be at least some mathematicians, some material scientists, and some chemists. But they made the call, and then you have to find your partners. So I think it's difficult, maybe it's possible, I don't know, to do it in a way as you described, like a website, and then there is a call for that. Maybe somebody with imagination, but I think it's more based on personal relations, talking to people.
Let's see, somebody wants to add maybe?
I think I did have some experience with this issue because for 8 years I was director of the national lab here in Brazil, National Lab on Scientific Computing. And as I used to define this national lab, I used to define it as a zoo of modelers. In other words, model everything, right? A bunch of applied mathematicians, computer science people, engineers, and oceanographers, and so on. And I think I had the same goal as director of this national lab. And I did a lot of getting together. In other words, I identified that, you know, this guy should talk to this other guy because I detected what was the point, I mean, the common point of interest. So usually what I did was to talk before with one separately to each one, and then at some point put them together. Because my first impression was that when I tried to start at the very beginning with both specialists at the same time, the initial conversation did not produce much results. But doing it first at a separate discussion and then getting together had a very positive impact. And I can certainly tell you that I had a lot of fun during those 8 years doing that.
Thank you. Let's see, there was somebody else raised their hand. Yes, please.
I'll try to keep it short. So my name is Henrique Saep. I'm from Unicamp, as my colleague over there. And I confess I'm a pure mathematician. Right, so applied mathematicians have a much easier time when they have to justify their job to wider society because it's just obviously both interesting and useful. It's fascinating. My background is in theoretical physics, but I always loved applied stuff. However, you know, a technical problem requires a technical solution, a political problem requires a political solution, but I think mathematics could contribute not only at the technical level, but at a sort of existential level as well. The sort of the thing that binds pure and applied mathematicians together is that we both communities love math. So what does that mean? We're particularly thanks to big data, or as a cause caused by big data, which is developed by applied mathematicians, we are rapidly evolving to a post-work society, at least in the developed countries. You know, in the United States alone, by the end of my generation, half of the jobs will simply disappear. They won't be outsourced, they'll just cease to exist. Right? So we are evolving towards a high productivity, few jobs economy. And then a natural question is, what happens to the free time? How do you redefine an existential ethics that does not rely on work and productivity? And the answer, I think, I suggest, is, of course, it's math. So we should do math. I'm a pure mathematician. I think math's a great thing to do with your time on Earth. It's a limited resource. We use it doing math, and look back, we don't regret it. What's the obstruction to this? The obstruction to this is this culture of usefulness. And this is why I think this debate has to be engaged with applied mathematicians as well. This notion that something is only useful if it serves some other purpose, right? So what is operator algebra good for? Oh, it's good because it helps engineers do something. No, that's not the whole truth. That's not why brilliant people do operator algebra, since we're in this audience. It's because it's great to do it, because it's very interesting and it's fascinating, right? So in some sense, the value of something gets transferred to something else that it serves, and the series of, this serves to this other thing, somehow it seems to terminate at an act of consumption, right? I do pure math because in 100 years it'll be applied math, and then it'll be engineering, and then somebody will build a factory that will build a cheaper shoe, which you can go to the shopping mall and buy. And then somehow people are satisfied. If I can terminate this chain at an act of consumption, then in our current sort of ideological approach, this seems satisfactory, right? But this is entropically unstable. We can't satisfy our needs, even if our material needs are satisfied by a post-war society. We can't all just consume to satisfy this sort of existential void, but we could do math. As something that has meaning in itself. So perhaps we could sell the sort of fascination of doing mathematics as something that is worth our time on Earth being well spent. And the prospect would be to build a post-work ethical framework of curiosity, discovery, collective learning, sharing, and rationality as opposed to obscurantism and so on. So perhaps as mathematicians, as a larger community, we could contribute to establish this sort of a existential project, as well as the very important project of applied mathematics solving concrete issues, which is great.
That's a very deep and interesting perspective on what it means to be even a mathematician. I think Maria has some comments, and then maybe we can hear from Claudia also.
Yeah, that's very interesting. And well, it's true that it's easier to explain the kind of mathematics, not the mathematics, the application of the mathematics we do. On the other hand, there is also some situation you don't face when you do pure mathematics. That is, you are happy when your paper gets published, let's say. Also, there is a big satisfaction and that fills the void, etc. But professionally, there is a paper that is published. In my field, there is also the fact that after you publish your paper, the practitioners will be using your algorithm, and then they may find mistakes and things, and you have to be very sure that things are okay. So this is something that sometimes is not seen, and it is also to be taken into account. Regarding, I don't believe in, regarding this difference between pure and applied mathematics, I don't believe in this difference except for those anecdotes, I would say. Because we are all doing what we are doing because we feel passion for that and it feels ourselves, and not because of some immediate compensation. It has been, for me, all the applications have always been a source for the deep thinking and new theorems and new theoretical results, existential results, things I wouldn't have thought of if it wasn't because of this particular application, because this is the way my brain works. I don't have so much imagination. So I don't see like opposition, I see like complementary those, the two branches, let's say, applied and pure mathematics. And we can all enrich each other by having this common vision of we are all in this area because we have passion for that.
And just to complete what Claudia said, I don't think that Vincent, when he was asking his question, he wants to justify what he does by asking, how can I help? I think that he really wants to help, and he wants to understand how to help in this endeavor. So I don't think he's looking for a justification. And also I would like to say that I'm less and less convinced also of the division between applied and pure mathematics. But I am very convinced that there is a difference between applied and pure mathematicians. There are people who like to work on a very theoretical, deep, conjecture, and they really are very happy doing that. There are other people who want to do mathematics to give some answer, more or less practical, to some concrete problem, and it's fine. There is room for everybody. I think that we have freedom in research, and people get pleasure from doing one thing and the other thing, and I think that everybody wants, and that's what he or she wants. There is room for everybody.
Edward or Amit, do you want to weigh in?
Yes, I think one distinction that happens in physics quite a bit is experimental physics versus theoretical. But there, such a question of existential questions don't arise pretty much at all, because the experiments are key for the theorist, and theories are also absolutely essential for new experiments and so on. So I see the role of applied mathematics and pure mathematics in a similar fashion, that the applied mathematics can come up with new mathematical ideas and concepts which then need to be developed as a purely mathematical object. And these interaction has to continue, I feel.
The question, by the way, reminds me of this famous quote by Hardy, in which he said that he was proud and pleased to have worked on number theory, his favorite subject, all his life, as a subject that was never good for anything and will never be good for anything, never have any application. And this was true for another 30 years or so, until RSA and Diffie-Hellman and other key exchange mechanisms and elliptic curve cryptography came around, on which our internet now is based. So he did not live to see the truth, but mathematics produces material sometimes which will all of a sudden become extremely useful. We just don't know when, but this has happened many times. Unfortunately, we cannot give this information to the funding agencies and the authorities, but we all believe in that, don't we? And it supports this idea that there's really no difference between applied and pure mathematics. Let's go on. Maybe there's another question from the audience.
Hello. Sorry. So it's just, I want to point out the fact that for me there is like an absent.
Would you just identify yourself?
Yeah, sure. Sorry, I forgot. So my name is Juan Pablo Vignon. I work in Paris, in Paris Diderot. And I just wanted to point out, for me, that like there is an aspect of all this that is kind of absent in the discussion, because effectively, like, part of the work of mathematicians is like kind of model and understand reality. And I think you talked a lot about that in a very good way. But I think we also, at this point, we create the reality we live in. I mean, internet, the computers are like a mathematical result, if you want. Also an engineering result, of course, but at the base is mathematics. Internet is mathematics. Bitcoin, for example, is mathematics, and nowadays is like a system that consumes more energy than Ireland, for example. And you have like a lot of examples like that of technologies that are like mainly mathematical and have huge impacts in like all the things you listed at the beginning. And for me, like, part of what we can do as mathematicians is to invent systems that don't work on the principles of the current society. And I don't know if this is a topic or not, but like, I think there are a lot of people like with a lot of talent that goes into finance, that goes into like more or less reproducing the same economical system that is producing all these things. And I see really, really much fewer people going into the equivalent thing of thinking like algorithms and systems and interactions between human beings that turn out to be sustainable and not just like profitable. And well, I don't know if you have some things to comment on that, but I don't think we're just observers of the world. I think we can also kind of create certain stuff. I don't know.
Let's maybe hear a couple of brief comments on that, and then I think we'll return to questions which I prepared. Amit, you want to start? Say something about whether mathematics, question was whether mathematics creates or discovers, is that maybe the way?
I mean, I think I don't really have much to comment except to agree that this is quite, so it's partly in answer to, of course, to your question as well. Another example I could think of just now after I finished my answer was if there were in the talks of, for example, Akshay Venkatesh and also I think I remember Akshay's talk for sure. He mentioned about several numerical observations which are then explained by the theorems or the kind of things that they're trying to prove are somehow motivated. They have some evidence. The evidence comes from numerical observations. Well, in that sense, I would call that applied mathematics as well, if you want to call it. The observation does not come from chairs and the world or trees or people. It comes from numerical observations. It is still similar. The method is very similar. Applied mathematics or mathematics. You have some phenomena. You are observing something and you want to explain it in a mathematically, logically coherent fashion. And I think that's basically probably what you are trying to say, my interpretation of what you are saying.
Edward.
Yeah, actually I agree with your comment entirely, and that's what mathematical modeling is about. After understanding the process, you have now to generate scenarios of what can happen, and that is far more important than even understanding the past, because we are looking forward. So I agree entirely with you. That's what mathematical modeling is about.
Thank you. Let's maybe one quick question, but please keep it very short because I want to be able to have another round for everybody here.
Hello. Yeah, I'm Nalini Anantaraman, working in Paris, and I just want to say that I'm not sure I understood in the same way as you did what he said. What I understood for what he said is that a lot of the mathematical activity that is currently done goes in the opposite direction to the stability of the planet. And I think, is that what you said? Yeah. So he was saying that a lot of the mathematical efforts that is currently done goes not in the direction that we think is good here, but he was talking about finance, about trying to improve the profit and things like that. Is that what you meant? So I think, yes.
I think it's clearer now, yes. There's this quote that the brightest minds of the generation are focused on getting more eyeballs on websites, which is, maybe that's what you're saying there. So perhaps we can go to a question here about how to train the next generation of mathematical scientists, many of whom are in the room here, to have, well, here's the question, right? How to engage students or beginning researchers, how to train the next generation of mathematical scientists to work on real problems, shall we say. Maybe that will help also answer this question. So this is the question. We have about 6 minutes left, so maybe all of our panelists can briefly comment on that. 1 minute per person.
I think we have done a good job, so far. We have several challenges, in Africa. We are looking at human diseases, animal diseases. We are looking at preserving, our ecology. and so on. So we have students working in those areas. But what we have gone much further than that. We have now invited our colleagues, mainly from the US, and a few from the UK, who are working with our students, so that our students can also have an outlook, an overall outlook of how things are being done in other countries. And I must thank the Simons Foundation. They have been funding this project. So we are engaging our students, and we are working on the problems that are facing our continent. Thank you.
I think that something that could be done, and maybe it's done in some places, is to design curricula for this kind of work. So it can be done not at the level of a university of a country, even at the international level, to design curricula for people, the students who want to go into that direction, what they should learn, and offer courses in those directions.
I think one thing that would help tremendously would be to make the parallels between the pure maths and applied maths work very explicit, and make it clear that both of these are actually mathematical problems that you're looking at, different types of mathematical problems, but they're still the same mathematical reasoning, and that will help, especially in a country like India where pure maths is still very much highly respected, but applied maths not so much. And that reducing that distinction will go a long way in getting more students interested in addressing these kind of problems.
I don't have a general question. I can just share my own experience. For students, for the advisor, it's important to have good students. For the good students, it's important to have funding. And then for that, you need to put in your list of research topics something that is fashionable. Before it was finance, now it is machine learning or other topics. This is a reality we have to live with, but this doesn't mean that we will only be doing that. But this is just a personal thing that each one of us can a little bit contribute in that direction. I don't know if we can have some general statements to answer to your question. It is not easy to change those trends. The only thing of those trends is that they pass, and there is a new one that comes afterwards. So this is my response.
I would also like to bring a personal experience that in order to engage students on planetary challenge studies. I think it needs a special effort to train high school teachers. We have a very successful example in our institute that came from the Department of Astronomy. They started doing that very intensively, training professors, teachers at the high school level about 8 years ago. You know what was the result? Now we start getting very good students that are admitted in our program because they went through a public school with these teachers who were got engaged in training courses given by the astronomers. I find several cases, success cases of the new students with this kind of background.
Thank you. Maybe as a moderator, I will also weigh in now on this question. Perhaps what we've heard here is that the earlier you start with this, but the younger the students are, which includes primary and secondary school students, the better it is. And then a multiplier effect is important. That may include training teachers or having engaged professors who are willing to work with students, who are willing to take on a new topic and engage in particular students who are coming in, even at the college level, who don't quite know yet about all these supposed distinctions between different disciplines. They don't know that yet. One should not drill them so that they think about these differences. One should keep their minds open and encourage them to stay broad. And finally, from my own experience, I can only say you can only offer it to the students if somebody decides to then work on something else. They will still hopefully had a very good experience where they saw an application of mathematics during their studies that really matters, and they will not forget that even if they work in something else afterwards. So we have 40 seconds left, so I don't plan to keep you here much longer. It's late. I would like to thank the audience, and I would like to certainly thank all the 5 panelists here for their great answers. Thank you very much, and have a very good evening and rest of the conference.